Inside the engine, we mix air with fuel. We need about 15 parts of oxygen for each part of fuel to make a complete combustion, where all the parts of fuel in the cylinder are burned and no oxygen or fuel are left after the combustion. The 15:1 ratio mass is called the stoichiometric ratio. When you're running the engine at the stoichiometric ratio, the exhaust gas temperature is maximum. It is said that the engine runs at peak. We have here the exhaust gas temperature as a function of the fuel flow. Starting from peak, when we reduce the fuel flow, it is said that we are lean of peak, in short LOP. When we increase the fuel flow, it is said that we are rich of peak, in short ROP. 60 degrees LOP means that we have leaned the fuel flow starting from peak until EGT temperature is reduced by 60 degrees Fahrenheit or Celsius depending on the context. 200 degrees ROP means that we have increased the fuel flow starting from peak until EGT temperature is reduced by 200 degrees. We do not want to run the engine at peak point because the engine would be damaged by excess heat. This is why we prefer to run the engine either in the LOP or ROP domain in order to reduce the engine temperature. The strength of aluminum alloy used in aircraft engines decreases as temperature increases. A big reduction in strength occurs at about 250 degrees Celsius, resulting in premature exhaust valve problems and increased cylinder head fatigue cracking. The red box is a domain where the engine is too hot for its aluminum parts, meaning too close to 250 degrees Celsius. If you go richer than 200 degrees ROP, in our example, the engine will be cooled enough by the fuel. If you go more than 60 degrees LOP, also in this example, the engine will be cooled down by air. In the middle, between 60 degrees LOP and 200 degrees ROP, you're damaging the engine, and you are in the red box. The limits of the red box, here 60 degrees LOP and 200 degrees ROP, are a function of the power which is required from the engine. Depending whether you have required, say, 80%, 75% or 65% of the maximum continuous engine power, we get different red box limits. This is an engine performance table of the RAEP Baron 58. There are all sorts of such tables which provide the main engine parameters, for instance for maximum, recommended, and economy cruise power settings. Let's see what we have in each column. Pressure altitude means pressure of the outside air, which is to say the intake air of the engine, corresponding to a certain altitude of the plane expressed in feet. The outside air temperature, in short OAT, refers to the temperature of the air around the aircraft. The manifold pressure is the air pressure inside the air manifold, in short MAP. The air manifold is a big pipe which brings the outside air into the cylinders. The manifold pressure is expressed in inches of mercury, in short INHG, Hg designating mercury in chemistry. This measurement is one of the best methods to determine just how much power is being developed by the engine. The more air and fuel we can pump or pull into the cylinders, the more power the engine can develop, which makes us fly faster. This is a fuel flow into the engine expressed in pounds per hour, in short pph, or US gallons per hour, in short GPH. 1 pound equals approximately 0.45 kilos, and the US gallon equals about 3.79 liters. The not indicated airspeed, in short KIAS, is the speed indicated by the airplane instruments, usually a Pitot gauge, expressed in knots. The International Standard Atmosphere, in short ISA, is a model of temperature and pressure across altitude. It was created to provide a baseline reference and is used as a basis for engine performance calculations. We check the outside temperature by calling the ATIS with a plane radio. In this example, the outside temperature is 18 degrees, therefore we are close to ISA conditions.
Sky conditions 4000 few, temperature 18, dew point -7. Area QNH1013.
According to the reference tables, we get the recommended running point, 20 degrees LOP, 2500 RPM, 25 inches of mercury, 4000 feet, 15.2 GPH, 186 knots. We adjust the engine parameters in accordance to the performance table. After the adjustment, REP tells us that we are inside the red box, which is surprising because it means that we are damaging the engine, although we have duly followed the manufacturer's instructions. This happens often because those tables were developed at a time people were not aware of the red box. It is convenient to assign joystick buttons for leaning a bit or reaching a bit the mixture very precisely. Changing a bit the throttle back and forth is a way to have REP displaying the current engine parameters. For a given throttle position, which is to say a given manifold air pressure, we reduce the mixture to get out of the red box. This avoids damaging the engine and saves a lot of fuel.